So today we're going to talk about mole ratio, and as the name implies, it is a ratio of moles within a reaction, within a chemical reaction. So here we have a little mole and a bunch of other moles on each side of the reaction, and there is a specific ratio between the moles of these reactants and these products, as well as a reactant to another reactant. Um, so, what is mole ratio exactly? It is the ratio of these different substances in moles, and the key point here is that it has to be, it will be found only in a balanced equation. And as long as the equation is balanced, all you need to do is take the coefficients of whatever substances are in question, and those will make up your mole ratio. Those will make up the moles of uh, of that substance, and from there you would understand the ratio of that one substance to another substance in moles. Moles can be used to measure the amount of substance needed, but also we can take those moles and convert them to mass, grams, and from there we can also find the amount needed of a specific substance. So the example experiment is we started with an unknown sample of copper dihydrate, and we used that to extract copper 2 plus ions. Then we had aluminum wire, which was used to extract aluminum. We filtered through filtration, we were able to extract copper, and then finally we titrated sodium hydroxide with aluminum to produce aluminum 3 plus ions. So those are the four main species involved in this example. Uh, like I said, we needed the ratio of copper 2 plus ions to aluminum to copper to aluminum 3 plus ions. So to start the process, we ended up starting with finding the mass of of we ended up first trying to find the moles of copper 2 plus. So we found the mass of the sample that we had, um, found the molar mass, from there found the moles of copper, of the hydrous copper substance, and then we were able to find the moles of the Cu2 plus ions. Okay, we needed then to find the moles of aluminum. Same process, we used the aluminum wire. We found basically the grams of the mass of aluminum that was reacted. We used the molar mass to calculate the moles of aluminum. Then we titrated uh, sodium hydroxide until the solution turned pink because of um, the dye, the pigment that was used. Um, at that point, it had reached the amount of a calculated amount of 0.00266 moles of aluminum 3 plus ions. Um, okay, so all of that was leading up to this. This is where the actual mole ratio comes to play. Um, the moles of each of the different ions was calculated, and then they were put in a ratio between that and the Cu2 plus ions, because we already know that the Cu2 plus ions in the reaction, um, there's 3 moles necessary. So these are the numbers we got for aluminum, the ratio between aluminum moles of aluminum and moles of Cu2 plus, moles of copper and moles of copper 2 plus, so forth, so on and so forth. And these are the after you multiply everything by 3, since the 1 mole of copper is actually 3 moles. These are the numbers we got. So 3 moles of copper 2 plus, obviously, which was not calculated, that was a given. 2.19 moles of aluminum, which is very close to the actual the theoretical uh, number. We needed 2 moles, and as you can see from there, 2.79 moles of copper, which is very close to 3, and 1.9, which is very close to 2. So as long as this kind of experiment is done right, you should get the balanced equation. Um, After rounding, of course, the balanced net ionic equation, and since this is a redox reaction, you can use that to help check uh, whether you know whether all the charges are balanced and if the ions are balanced and so on. Um, so again, this comes into play a lot. Mole ratio is not just for this kind of experiment, but there are many different uses. One of the key uses is for neutralization. Um, if you have a certain acid and a certain base, you want to know how much of that base, for example, is needed to neutralize that acid before you can dump it down the drain. Otherwise, you're gonna burn a hole in your sink. So you'd use that same process to understand how many moles, and then from there you can turn it into grams, liters, whatever, how much you want to do. But you would use that to get a definitive answer of how much of this base is needed to fully neutralize that acid. Like I said, you could check your redox equations with it. Um, it helps you understand exactly how many electrons are exchanged, and as long as it's symmetrical, then you're doing something right. And again, I mean, in daily life, it's a very useful concept. It fits into a lot of different aspects of life. Um, e- anything from cooking to chemistry uses this kind of concept. Example, when you're making coffee or something, you have a specific ratio of different ingredients: 3 parts coffee, 3 parts milk, whatever. So it's the same concept, and as long as you follow that ratio, then it should come out the same. The products of this reaction, or of this of cooking and that with those ingredients, should always come out to the same.